Hello students, welcome to next lecture. In this session we will be discussing single phase bridge inverter. Okay, so the full bridge here, it is simply called as bridge inverter. Okay, single phase bridge inverter. So by the end of this session you will be able to describe the operation of single phase bridge inverter with R load and RL load. Both we will discuss in this session. All right. So the circuit for single phase bridge inverter with R load is shown in the figure here. So as you can observe, there are 4 transistors and 4 diodes. The diodes are required for feedback when the load is inductive, in fact. So here, since the load is R type, so there is no role of the diodes D1, D2, D3 and D4. Okay. Since the bridge, full wave bridge, the setup is same for whether the load is R or inductive. The diodes are also shown here. Okay. So when the load is resistive, as I mentioned, the diodes does not carry any current here, and the operation of this circuit can be understood like this. So the transistor T1 and T2 say they will conduct between time instant 0 to T by 2. Okay, so let us observe the equivalent circuit here. So observe this is the equivalent circuit. So for time duration between 0 to T by 2, assume that the thyristors T1 and T2, or you can also call it as switches T1 and T2, when they are conducting, yeah, the current path in the circuit via T1 and T2 is shown here. So observe the output voltage and the current. Observe the output voltage and the current, both are positive, right? So the voltage is voltage across the load, that is resistive load. The output will be positive here and negative. So output will be EDC, yeah, and the current also will be in this direction. So it is also positive. Okay. So assume that at time instant T by 2, you have turned off T1 and T2 thyristors, and you have turned on T3 and T4. So observe the current path in the circuit will be like this via T3 through the load and T4 and back to the supply. So observe, our intention is to convert the fixed DC supply, and we want to have variable output across the load, right? So the objective or the operation, the principal operation, what we had observed in the initial classes, that at the load should be connected to the supply in one direction for say few time instant, and in the next time instant it should be connected in the reverse direction, right? So that is what is happening now. So when T1 and T2 is turned on, or when they are conducting, the current or the voltage across the load will be in this direction, here positive and here negative, as you can observe here in the equivalent circuit. When T3 and T4 are made turned on or conducting, then the voltage will be in the direction like this. So it will be reverse, minus EDC. So if your EDC is your fixed DC supply, then when T1 and T2 are conducting, the output will be plus EDC. When T3 and T4 are conducting, then across the load, the output voltage will be minus EDC. And as you can observe, the current direction also will be reverse in between the time instant T by 2 to the next time instant T, right? So from 0 to T by 2, as you can observe, when T1 and T2 are conducting, the output voltage is plus EDC. When between T by 2 to T time instant, when T3 and T4 are conducting, the output voltage is minus EDC. Yeah. So this is the first waveform. What you can observe here in the waveforms is load voltage, that is the voltage across the load. So as you can observe, it is square, right? Square wave is what you are observing. So similarly, the current also will be positive for the time duration 0 to T by 2, and it will be negative between T by 2 to T. So current value will be EDC by R, and here it will be minus EDC by R. Obviously, the magnitude is less compared to the voltage, right? Because it is EDC by R here for current. So as you can observe, this is a typical square wave output for single phase bridge inverter. That is, for resistive load, the voltage and current both will be in phase. What waveforms you are getting is both are square wave. Obviously, we know that there will be some harmonics present there. So if you want to have a smooth variable curve or the output, say if you want to smoothen the output, remove the harmonics, then you have to use filter circuits, right? So that is the operation of a single phase bridge inverter with R load. So obviously the other waveforms are for the switches, the current across the switches S1 and S2, S3 and S4, which you are familiar. So let us observe the equations for single phase bridge inverter. So here is the question: derive the following for single phase bridge inverter having square wave output. So first is to find the RMS value of the output, then Fourier series for output voltage, then RMS value of fundamental component of voltage. So first, to find RMS value of output voltage, it can be written as V naught RMS, that is output voltage, right? RMS value of the output voltage, V naught RMS, it can be written as 1 by T for complete one cycle 0 to T, the output voltage V naught square with respect to d omega T, which is under square root, right? This is RMS, root means square of the output voltage. So since we know that the bridge inverter output is also square wave, similar to the half bridge inverter, the only difference here is the square wave has the amplitudes plus EDC and minus EDC. Whereas in half wave bridge inverter, we had plus EDC by 2 and minus EDC by 2. So in the above equation now for the output voltage for the complete one time period 0 to T, splitting the output here, we can rewrite it as V naught RMS is equal to 1 by 2, that is under the square root. Splitting the output there between 0 to T by 2 and T by 2 to T. So 0 to T by 2, it is EDC square plus T by 2 to T, it is minus EDC square, right? So when you take EDC outside, EDC square outside, EDC square by T, so inside you will be, you are ended up with 0 to T by 2 limits with respect to dt and T by 2 to T with respect to dt. Of course, everything under square root. So if you observe that, finally, when you apply, after integration, when you apply limits there, inside the bracket you will have T by 2 plus T minus T by 2. So T by 2 and T by 2 gets cancelled. So inside the bracket you will have T and outside you have T here, which both get cancelled. So under the square root you will have EDC square. So finally you will have the RMS output voltage which is equal to EDC. So thus the RMS value of the output voltage is same as the DC supply. Okay. Now coming to Fourier series for output voltage. Since the output waveform for both half bridge and full bridge are square wave, we knew that the half bridge square Fourier series was given by V naught omega t, where we had only odd harmonics there. Remember, 4 into EDC by 2 by n pi sine n omega t. So this is the equation for half bridge inverter. So substituting uh, the input voltage there for full bridge. So it will be 4 EDC by n pi sine n omega t. So the above equation shows that the output voltage contains only odd harmonics. So similar to the derivation what we had in half bridge inverter, kindly go through the previous session if you want to know how we got this equation. Okay. So since both the outputs for half bridge and full bridge, it is square wave, only thing we are replacing here is the input voltage. Okay, input DC supply. Fine. So coming to RMS value of fundamental components. So in the above equation, in the Fourier series of the bridge equation, if we substitute n is equal to 1 is what we will be getting fundamental component, right? So substituting n is equal to 1, we get V1 omega t is equal to 4 EDC by, instead of n pi, it is pi sine omega t. So this is the same, this has the same frequency as that of the square wave. So the peak value of the fundamental, it is given by C1, which we know that it is given by 4 times EDC by pi, right? So the RMS value of the fundamental component is given by V1 RMS, which will be equal to C1 by root 2. Okay, substituting C1 there, C1 is 4 EDC by pi by root 2. So it will be 4 EDC by root 2 pi. So which is equal to 2 root 2 EDC by pi. Okay, so taking the value of 2 root 2 by pi, you will get 0.9. So the fundamental RMS value of fundamental component, that is V1 RMS, it is given by 0.1 times EDC. Okay, so this is the RMS value of the fundamental component. So for nth harmonic, we know it is nothing but dividing it by n. That is 0.9 EDC by n will give you the RMS value of the nth harmonic component. For example, if it is asked to find the harmonic second, third, fourth, fifth harmonic component, then you have to substitute n value here. Okay, for second 2, third 3, fourth like that 4. So the RMS value of nth harmonic component, it is given by Vn RMS, which will be equal to 0.9 times EDC by n. We can also write it as V1 RMS by n. V1 RMS is nothing but the RMS value of the fundamental component. So these are the different equations that we have to go through for single phase bridge inverter. Now, continuing with the bridge with RL load. So if your bridge is a full wave bridge has inductive load, then the circuit would look like this. The circuit, the bridge circuit remains same, where you have T1, T2, T3 and T4, and along with that you have diodes D1, D2, D3, D4, which are the feedback diodes, and as you can see, the load is inductive. So let us observe how it works. So say for example, when T1 and T2 are conducting between the time duration T1 to T by 2, assume that for time instant T1 to T by 2, say time some instant, you have turned on T1 and T2. So observe how will be the current or the circuit operating from EDC via T1 via load T2 and going back to EDC, right? So observe the direction of the voltage and the current here. So say after T2 or at time T2. Now you are turning off T1 and T2. What happens? Because of the nature of the inductor, now the voltage that is stored, or the energy that is stored in the inductor, now it has to be dissipated. So it reverses its polarity, right? So when it was getting charged, or when the energy is getting stored, the potential at this point was positive and negative at the inductor. Once T1 and T2 was turned off, because of the property of the inductor, the polarity reverses, right? So as you can observe here, from between T2 to T by 2 to T2, now the polarity has reversed. So the energy that is stored in the inductor is now getting dissipated. So this leakage current, that is the energy that is now getting dissipated by the inductor or the load, which has to be fed back to the supply. Okay, so the current or the current path will be via D3, going back, getting the energy fed back to the source, and D4. So D3 and D4 will conduct during that period. I hope you are able to understand. So say that the energy that is stored is completely fed back to the supply. Now the current has become zero. Now in the next time instant, say at small t2 time instant, now you're turning on T3 and T4. So when T3 and T4 is turned on, now again the current direction will be like this, from EDC via T3, observe across the load, the current path will be in this direction, T4, and coming back to the supply. So the direction of the voltage and the current will be in this direction, right? So now the both the current and the voltage are in the reverse direction. So now again reverse, and both are in same direction. So energy is again getting stored in the load, right? So after, say, at time instant t, okay, you're turning off T3 and T4. Now what happens? Now again the polarity at the inductor will reverse now. So initially at this stage it was positive here and negative here. So once T3 and T4 is turned off, now the polarity at the inductor will be positive here and negative here. So it has to dissipate its energy, causing D1 and D2 getting forward bias. So the current will be flowing in this direction. D1 will be forward bias. So the energy will be fed back to the supply via D2, like this, in this fashion. So that is how the working of the single phase bridge inverter for RL load. Kindly go through. If you have any clarification in this, you can ask. So the RMS value and the remaining equations will be same that of what we had discussed for the half bridge. So I will leave it to you to find out or get the determine the RMS value of the output voltage and the fundamental component, etc. Okay, for RL load, obviously for RL load. So see you in the next session.